Good morning, students. I'm Dr. Raja Anita, Faculty for Artificial Intelligence. Today we are going to learn the session number 9, that is alpha beta pruning. Before we are going for alpha beta pruning, let us recall the topic what we discussed earlier, that is min-max algorithm. So in session number 8, we discussed about min-max algorithm. So what is the drawback of min-max algorithm? Why and how we are going to overcome that drawback in alpha beta pruning? So first of all, what is an alpha beta pruning? This is an advanced version of min-max algorithm. Before we are going to learn about pruning, let us discuss the drawback of min-max algorithm. The drawback of min-max algorithm is that it explores each node in the tree deeply to provide the best path among all the paths. So if you want to find out the best path in min-max algorithm, we need to explore each and every node in the given path. So what it will happen if you are exploring each and every node in the given path, automatically it increase the time complexity. So when you can say that your performance is good, if the time complexity is less, then you can say that the performance of that particular algorithm is good. So to decrease that time complexity, we are going for alpha beta pruning. In this alpha beta pruning, we are using the method of cut off the search. That means we are not exploring some nodes which it is not necessary. That it is called it as pruning. Unnecessary searching or unnecessary exploring the nodes, we are not exploring it. Just we are pruning it. So that's why we are calling it as alpha beta pruning. Why the name is alpha beta pruning? So in a game playing, we are having two opponents. So one opponent we are calling it as max and another opponent we are calling it as a minimum. So if you are decreasing or if you are not exploring any node of a one player, that is called alpha pruning. If you are if you are applying the pruning on opponent, you are calling that is a beta pruning. Understood? Here we are having in a gameplay two players. For example, we are talking about the two-player game. In the two-player game, we are having two players, max player and min player. So if you are applying, if you are not exploring the node that it is belongs to the max player, that is called alpha pruning. Next, if you are not exploring the node that is belongs to the min player, that is called it as beta pruning. Okay, here we have these alpha and beta are two threshold values. So let me give an introduction about alpha beta pruning. Alpha beta pruning is a way of finding the optimal min-max solution. Yes, we are finding the optimal min-max solution. Why we are going for alpha beta pruning? To reduce the drawback of min-max algorithm. What is the drawback of min-max algorithm? In min-max algorithm, it is exploring each and every node even though that exploring of the node is not necessary. So what it will happen if you are exploring like that, automatically the time complexity is going to increase. So because of that reason, we are going for alpha beta pruning. So in the search tree for a two-player game, there are two kinds of nodes. So what are the nodes we are having in min-max algorithm? We are keeping the name as max player and min player. Suppose you are playing the game, you are the max player, the opponent of that player is called it as min player. Okay, alpha beta pruning gets its name from two parameters. So why we are giving the name as alpha beta pruning? Because of two threshold values or two parameters. Those two parameters are alpha and beta. So alpha, this alpha always the value of the best choice found so far along the max for max. That means always the path it has to be the max. So alpha is always trying to increase the value of max. That means it is always trying to increase the winningness of the game, whatever we discussed earlier. And beta is always the lowest value. That means minimum value. Beta is always best for the lowest value. That means beta always trying to decrease the chance of winningness of max. Max is trying to win the game, and minim is trying to decrease the winningness of max, so that we are calling it as alpha and beta. Now here alpha beta pruning gets its name from two bounds that are passed along during the calculation. Already I told for you those two bounds are alpha and beta. One is the maximum and another one is the minimum. Alpha is the maximum lower bound for all possible solutions, and beta is the minimum upper bound for all possible solutions. Okay, here the constraint that was given as alpha less than or equal to n less than or equal to beta. Right? Here n is the current estimate of the value. What is the current value of the node? So always the current value of the node, based upon the current value of the node, you are going to decide what is the alpha value and what is the beta value. Now you are going for algorithm. So before you are going for algorithm, you should be aware of that min-max algorithm. So I think you are very clear about min-max algorithm. What we did in the min-max algorithm, in min-max algorithm, we wrote two functions. One is for to find the maximum value, other one is to find the minimum value. So, but only the difference between min-max algorithm and alpha beta search is, in min-max algorithm, you are exploring each and every node in the depth of that node. But in alpha beta algorithm, we are just excluding the exploring of the depth of the node if it is unnecessary. So based upon that, you are reducing the time complexity. So here I am writing the function for alpha beta search. So what you are passing the parameter state. What is the current state you are passing as a parameter, and the return value is action. What the action you want to take, that is the return value. What are the inputs you are passing? State, current state in a game. What is the current state in your game? And v. So here we have one parameter v. So for that v, you are trying to find the maximum value. How we are going to, what are the initial values of max value and min value? The max value, the initial value of max value is minus infinity. The initial value of min value is plus infinity. Why we are giving minus infinity and plus infinity? Because beta value always trying to decrease and alpha value always trying to increase. Because of that, we are giving initially the values of alpha and beta is minus infinity and plus infinity. Now return the action in successor state with value v. So if you are finding the maximum value, then just you are returning that maximum value. And this is the function for max value. In this max value function, the name of the function is max value, and the parameters you are passing is state, comma alpha, comma beta. State is the current state and alpha is the current maximum value and beta is the current minimum value. It returns the utility value. What is the utility value? The utility value is one that specifies what is the output of that. So if you win the game, the utility value will give the value 1. If you lose the game, that value will be minus 1. If the tie occurs, the value will be 0. Okay. If terminals test, suppose if you reach to the terminal, that means you reach to the goal, then we can say that the utility value is 1 if you win the game, minus 1 if you lose the game, 0 for draw of the game. And first v is assigned to minus infinity. Why we did here this? Because we are finding the maximum value. The initial value for the maximum value is minus infinity, that was given, and for successor. So this is the main theme where we are doing. So this is the main thing you have to understand. First you have to find out the maximum value in the current state to the minimum value for the rest of the state. If it is greater than or equal to beta, then you are returning that value. Otherwise you are assigning the max value. So here you are applying the pruning here. So if it is greater than or equal to beta value, there is no need to go for further search. That's why it is giving it as if v is greater than or equal to beta, then you are directly returning v, right? And next, so this is the function for min value. So in min value also the same parameter you are passing. The only difference here is your v is assigned to plus infinity. Why? Because the minimum values always try to decrease the value. So we assigned plus infinity. And here the only difference here, here we are checking v greater than or equal to beta, then you are returning v. Here we are checking v less than or equal to alpha, you are returning v. So this is the algorithm. First I would like to explain this with the help of a example so that you could able to understand this algorithm very clearly. So before we are going for this this example, let me take another example. I will show you that procedure of alpha beta pruning in that example. So after you understand that example, you can apply the same procedure on this example. Let me take you to the board. Wait a minute. And here I am taking one example, and I would like to show you how we are applying the pruning procedure here. So for that I want to take an example for you. So here I am designing a tree. So you can clearly understand this. So how we are applying the alpha beta pruning here. Now I am taking a tree here. This is a tree and I am applying alpha beta pruning on this. So here I am specifying the nodes, and these are the different nodes I have, and I want to give the values also for each node. This, and here I am giving the value 3, 4, and this is 2, and this is 1, and this is 7, and this is 8, and this is 9, and this is 10. These are the leaf values. 2, and this is 11, and this is 1, and this is 12, and this is 14, and this is 9, and this is 13, and this is 16. So I gave all the leaf values here. So who is the first player here? Max is the first player. So I am treating it as alpha, as I told for you. So this is alpha. And next one is, who is the next player here? First, the game always play as per alternatives. So first, if you give the chance for the max player, the next chance it will go for the min player. So next chance we are going to give for the min player. This is the min player, and this is beta. Next, the next chance we are giving for max player. Here we are giving the chance for max player, and here we are giving for min player, right? So this is the way how the game is playing. So first max, next min, next max, again next min. Now how we are applying this is a alpha beta pruning. So first, as I told for you, we are following here DFS, depth first search. So as per the DFS, we are moving from the root node towards to the leaf node. So I moved. So here I found 3. Now here from this, which is the minimum value here? 3, 4. 3 is the minimum value. I wrote 3. Next, here if you are writing 3 in min-max algorithm, just you are going for the next subtree and you are finding the minimum value. Then from these two values you are finding the maximum value. But here you are applying the alpha beta pruning. In this alpha beta pruning, so first go for this side, and here you are able to see 2. So directly write 2 here. So whatever the value you are writing 2, this value always less than or equal to 2. Because we are selecting the minimum. This always greater than or equal to 3 because we are finding maximum. So here whenever you are writing this always less than or equal to 2 and this is always greater than or equal to 3, then what is the need to explore this one? No need to explore this one. Just you are applying pruning here. Pruning. So here you are applying pruning. This is beta pruning. You are applying the beta pruning. Are you understood? I am repeating once again. Here max, min players. These are the leaf nodes. Right? First you are taking the leaf node 3 and you are writing 3, 4. The minimum value is 3 you are writing. Next you are going for the right subtree of this. Here 2, 1 is there. Actually in min-max algorithm, in 2, 1 you are taking what is the minimum value and 1 you are writing. But here I don't want to explore because I want to apply the pruning. For that reason I am taking here 2 directly. Here 2 is there. 2 directly I am taking here, and I know that the value what we are expecting here is always less than or equal to 2 because this is the minimum. And I know this value always greater than or equal to 3 because the maximum value I am taking. But this is less than or equal to 2. Then what is the need to prune? What is the need to explore here? So I am just pruning this. I am not going to this part. Next, come down here. So you are going for for leaf. So I went to leaf 7. So 7, 8. Which one is the minimum here? 7 is the minimum. So here 9. So always it should be less than or equal to 9. So it should be here max. So which one is the max here? So in this 7, 8, 7 is the minimum. And here 9, 10, always it should be less than or equal to 9. So always it should be greater than or equal to 9, right? Always it should be greater than or equal to 9 because we are taking this is the max. So always it should be greater than or equal to 9. But here minimum means always it should be less than or equal to 3. But here 9 is there. Then what is the need to explore this? Just I am pruning this. Prune it. Next. Go for 11. 12, 2 and 11. So which one is here? 2 is the minimum. And if you are going for this, is always it should be less than or equal to 2. Right? So 1, 12. So here I am taking 1. Always it should be less than 2. So maximum means it should be greater than or equal to 2. So if it is greater than or equal to 2, then what is the need to prune? Just here explore. Pruning is done. Pruning is done. Next you are going for, this should be greater than or equal to 2. And here this is the minimum 9. So it should be less than or equal to 9 and it should be 13, less than or equal to 13. It should be greater than or equal to 9. So right, maximum value taking. If it is greater than or equal to 2, I mean here minimum less than or equal to 2. So no need to take greater than or equal to 2. Just you are prune this. So I am pruning of this. And it should be greater than or equal to 3, right? So you are taking the best path. This is called alpha beta pruning, right? So I'm explaining this again for you for your understanding. By giving simple example, I'm taking this. Suppose this is the node. I'm taking simple example instead of taking lengthy example so that you could able to understand clearly. First I explain with lengthy example, then I would like to explain with a simple example, right? And here your the values, this is the leaf values. Suppose this is a 3 and this is 4 and this is 4. 3, 4 and this is 5 and this is 6. This is 1, this is 3 and this is 7, 8, right? Here this is the max because the first player is max, this is alpha, and next player is min, next player is max, right? Now first you are going for depth first search tree. So you are going towards to this, and what is the terminal? 3. So max. So it should be always, so here I am writing 3, 4 is the max. 4 is the max. Here 5, 6. So here I am not taking the max value of 5, 6. Just I am writing 5. It should be always greater than or equal to 5. So I am expecting that this value here is always greater than or equal to 5. So this it should be less than 4, less than or equal to 4 because minimum. Then what is the need to go for this? Just I am pruning. Just I am not going to explore these nodes. And next same manner. Here 1, 3. So what is the maximum value? 3 is the maximum value. I am writing 3. So greater than or equal to 3. And here 7. I am taking 7. Always it should be greater than or equal to 7 this value. So minimum. So it should be less than or equal to 3. Then what is the need to explore this? Just I am pruning this. Prune. I don't want to explore. And max value. So here this is less than or equal to 4 and this is less than or equal to 3. What is the maximum? Always it should be greater than or equal to 3. So here that means maximum value. This is less than or equal to 4 and this is less than or equal to 3. So always it should be greater than or equal to 4. Then no need to explore this one because always this is less than or equal to 3. So it is greater than or equal to. So it is the best path. I am giving this is the best path. Understood? This is called it as alpha beta pruning. Now I want to show you in our PPT example. Let me go to our PPT. So this is the PPT example. In this PPT example, you have 3, 17, 2. You can clearly understand now. This is an example. It was given and we want to apply alpha beta pruning on this example. So first you are assigning beta equal to initial values. So what are the initial values? Beta equal to infinity, alpha equal to minus infinity, because these two are the threshold values we are giving. Next, so that was initially assigned for each node. Each node it was assigned initially. So that's what I am assigning, and I went for the last terminal. What is the terminal node here? Leaf node 3. So here, who is the player here? Suppose if you are taking, this is a max player, max min. This is the minimum player. So he has to select the minimum value from the given elements. So 317. Which one is the minimum value? 3 is the minimum value. I wrote 3 is the minimum value for beta because beta is playing here. Minimum player is playing here. So he select always the minimum value. 3 is selected here. Beta value is assigned for 3. And now this side, whatever you are expecting, what is the next node here? This side. So we have the node is, the next node is 2, right? So here the next node is 2. So I don't know who is the what is the next node of the next node of this node. So I know only 2. So I don't want to explore the right hand side of this node. So here I'm expecting the minimum of I mean always this value should be less than or equal to 2, isn't it? Always this value it should be less than or equal to 2, and minimum value. So we need to take it as minimum. So always here alpha 3, why I wrote, I need to select the maximum value between these two. So beta value is equal to 3 and here beta value is equal to infinity. I don't know. But here always I need to select the maximum value because here the max is playing the game. So whenever you are trying to find the maximum value here, you should understand here this value always less than or equal to 2. So here no need to prune this, no need to explore. So I am just pruning this. No need to explore the rest of the part. Just I am pruning. I know here this value always it should be greater than or equal to 3. So but here we found less than or equal to 2. So here only I identified the rest of the tree is less than or equal to 2. So just I pruned it. Next slide. Go for this. So what is the next slide? Here I applied pruning. So I'm not exploring from here onwards. I understood. So alpha values are always greater than or equal to 3. Then what is the need to prune this? So sorry, what is the need to explore this? So I pruned it. So just I wrote like this. The next one is here, next value. We are going for the next value. So here 3. So the next turn here is here. That means beta is playing. Whenever beta is playing, we know that this value always it should be less than or equal to 3. So go for the right hand side of that exploring the tree. So whenever you are going for the right hand side, this value it should be always less than or equal to 3. So if you are finding this, just I came to know beta equal to 3, it should be greater than or equal to 3. So here 15 is there. So you are writing 15. So this is the minimum. So it should be less than or equal to 15. Once you are finding this is less than or equal to 15. So no need to explore the rest of the part because I need this is always greater than or equal to 3. But here it is always it should be less than or equal to this number. So I don't want to explore. Just you are leaving that. Understood? Here just I'm not exploring this because I came to know that this is 15, but here the beta value is always less than or equal to 3. Then what is the need to explore this? Once you are starting your exploration, always these values it will become as greater than or equal to 15. No need here because the beta value always less than or equal to 3. So I got it as beta equal to 3. The next one is so go for the next tree. So if you are going for this side, here I know that the alpha value here is the max player. So if you are taking the max player means always it should be greater than or equal to 3. So you are coming towards to the this side. So I got the node as 2. So 2, this is the minimum. So it should be always less than or equal to 2. So whenever you are taking this is always less than or equal to 2, then you are going here, the max always it is greater than or equal to 2. So here no need to explore this side. So just you are applying the pruning. So that's what I'm writing here. So next one is go to the right hand side. In the same manner you are applying the procedure here for the rest of the slides. So what it will happen here is you are applying the pruning here, and then you are stopping to explore unnecessary searches. So whenever you are stopping to explore unnecessary searches, that means the time complexity you are reducing. So you are reducing the time complexity, because that is the one and only one decides the performance of the algorithm. So we are increasing the performance of the algorithm by decreasing the time complexity. So if you are not exploring this, that means you are reducing the time complexity. So based upon this, you are selecting that the drawback of min-max algorithm you are overcoming here. Right. Next, finally, here you could able to see this diagram, the alpha beta pruning. Think all of you understood. I want to give another example how we are applying the alpha beta pruning. So here let me go for the board, and I would like to give another example for your better understanding of alpha beta pruning. See here, I am taking a node here, and then here I am taking another one, and now simple example I am giving, so you can be able to understand. This is max and this is mean, right? And here I am giving 5, 4, and this is 6, 8. Right, now you have to go for the leaf node 5. So which one is the minimum? 5, 4. Here is the 4 is the minimum. Next here 6 is there. So next you have to go for the right hand side. And 6, 8 is there. But you should not compare 6, 8, because we are not doing any exploration of this. Just you are taking 6, because this is a 6 is a leaf node. Always it should be less than or equal to 6. Less than or equal to 6. But here max is we have to take it as greater than 6. That is, you have to select it. Greater than or equal to 4 you need to select. Right? This is less than or equal to 6. So we are not pruning. This is a greater than or equal to 4. So you are taking this one as the best path. Instead of pruning this one, just you are pruning this one and you are going for select the best path. So you are not exploring in depth of the each node. Just instead of that you are stopping where it is unnecessary. Right, this is about alpha beta pruning. So here the conclusion is pruning does not affect the final result. That's it. So don't worry about that. If you are not exploring each and every node, it may cause for any effect of the final result. No, definitely. Even though you are applying the pruning, it does not affect any final result. Entire subtree can be pruned, not just leaves. We are not pruning only just leaves. Entire subtree you can prune it. So no need to explore the entire subtree if it is unnecessary. Good move ordering improves the effectiveness of pruning. Yes, if it is a good move, it is improving the effectiveness of pruning. And how you are decreasing the time complexity instead of what is the time complexity for min-max algorithm? The min-max algorithm time complexity is big O of b power d. Then how we are reducing the time complexity? Here big O of b power m by 2. This is the time complexity. We can reduce the time complexity with effect from the branching factor of the square root of b. Right. Next, forward pruning. What is the forward pruning? Some moves at a given node are pruned immediately without further consideration. So we are not going any further consideration. Just you are removing immediately, and you are pruned immediately whenever you found that node is not necessary. That is called it as forward pruning. So here in the forward pruning, some moves at a given node are pruned immediately without further consideration. Yes, that's I explained just now. These kind of pruning is called it as forward pruning, and human playing chess consider only a few moves from each position, right? So whenever you are playing the chess, then it may occur. So immediately, whenever that set is not necessary, you are just stopping the moving of that step. That is called it as forward pruning, right? And beam search, that's what we discussed, local beam search, and best moves rather than the all possible moves. So that what is the beam search, local beam search? In n possibilities, randomly you are selecting one possibility, right? And probability cut. This is the probabilistic cut algorithm. This is a version of alpha beta search and gain previous experience. With the help of the previous experience only, it will decide the further step. For example, you and me are playing a chess game. So how the moves it will be, that is based upon your previous experience. So if you are finding that this is the move I have done earlier, then you can do that step here. That is called it as previous experience. Next, here generate and forward pruning. Here it was given somewhat introduction about forward pruning. It generates and evaluates around a million nodes on the latest PC, allowing us such roughly 200 million nodes per move. Understand time controls, and here it has to understand what is the time controls. Time limit it was given. Based upon that, it is allowing nearly 200 million nodes per move, right? And next, cutting off search. That's what we are calling alpha beta pruning is for cutting off search. So we are applying the cutting off search. What it mean, the cutting off search? So just you are not searching for further, you are not exploring for further, just you are cutting off the search. That's why we are calling this is a cutting off search. So here we can also write the function as if cutoff test state comma depth, then return evaluation value. This is e value function, estimated value function. This is a evaluation function, or we can say that evaluation function. What is the evaluation function? It will return for you if you are applying this cutoff test. Next, cutting of search, we can also call it that. Next one is quiescent. It's more sophisticated cutoff test is needed. So for quiescents, to exhibit wild swings in a value in near future. For example, if you some favorable catches are not in a quiescent for evaluation function, just you can apply these quiescents, and non-quiescent positions can be expanded further until quiescent positions are reached. Suppose if you are not finding the good moves, then you are stopping there. This extra search called quiescent search or certain types of moves resolve uncertainty in position. But because I don't know, I suppose you are playing a chess, so there is an uncertainty. It will happen. I can't able to decide where to move. So I just stopped. I didn't have my mind is not working because you are playing the mind games, not luck factor games. So uncertainty, there is no certainty for my step. So for this kind of problem, I mean positions, you can go for quiescent search. And next, horizon effect. The horizon effect is difficult to eliminate. So sometimes it is not. Sometimes we may face the horizon effect. So these kind of effects is very difficult to eliminate. When program is facing opponent who causes serious damage and avoidable, but temporarily avoid delay tactics. Suppose the steps, there is a damage for the steps. If there is any damage occur for the steps, that is called it as a horizon effect. In that kind of horizon effect, we cannot do anything and we cannot eliminate. And next, a singular extinction. To migrate the horizon effect in a singular extinction, a move is required that is clearly better than all moves in the given position. So if that is any damage it was occur for the opponent step, then you are saying it is very clearly better to move from singular extinction, move from horizon effect to the singular extinction. So course of search, the single move is remembered. So we have to remember the single move, and search reaches normal depth limit. Algorithm checks if the single extinction is legal move, and algorithms allows to consider. Suppose that the step what it was given by the opponent is illegal, it has to check if there is a legal move or illegal move. If there is an illegal move, it doesn't consider. It has to decide whether that is a legal move or illegal move, then it is moved to the horizon effect to the singular extinction. I think you are very clear about alpha beta pruning. So I would like to give the conclusion of this session. So we have to understand first why we are going for alpha beta pruning. The first thing here is in min-max algorithm we are facing a drawback, that is unnecessarily. Even though that is not necessary, we are going to explore each and every node. Because of that problem, the time complexity is going to increase. So to reduce the time complexity, we are going for alpha beta pruning. In alpha beta pruning, we are just pruning that unnecessary searches. How we are going to prune that unnecessary searches? Already we know that what it will be the next value of min or max. Based upon the min or max, you are going to cut off that search. So you are not exploring the rest of the subtree. You are not only exploring the leaves, but you are not you are pruning the entire subtree also. So this is the what we are doing in alpha beta pruning. Think you are all understood, and if there is any doubts for you, you can meet in a class. Good luck for you all.